Folks, here we go. Time for a little calculus. Let's see. So today's big day. Today we're going to chain roll. Chain roll. It is a chain roll. So the chain roll. Let me put this in a little perspective before we do it. Chain roll just takes. It doesn't really add anything. There's no new formulas, but it takes every standard form that we have for a derivative rule, and it just makes it way better. It just allows you. It makes them much more versatile. Allows you to attack, more complicated functions. Essentially what it does is it allows you to differentiate functions that are compositions, where you have functions of functions, right? Now we can't do that. Now we're just limited. We can do a sine x, but we can't do the derivative of sine of, say, x squared, right? That's not available to us. So today we crossed that threshold where we can do stuff like that. But before we get into, and so ultimately our goal is today, 95% of what you do with the chain rule is just use it to solve derivatives. And so we want to get to a point today where we can actually do some of those and look at some examples and kind of get used to how you think about differentiating a composition of functions. It sounds complicated, it's no big deal. You'll get into kind of a pattern with it, a flow with it, and it's not that hard to do. But conceptually, I want to sort of build up the chain rule first, just conceptually, because it's interesting the way it works. Let's take an example. Now, this doesn't work as well as it used to back in the day because we used to have analog clocks. So you have to use your imagination a little bit. We're going to just think about a clock for a second. If we think about a clock, let's define some variables. Let's say that S of t, that's the position function. So we're going to call that the angular position of the second hand. Okay, let's call M of t position of the minute hand. And what's h of t going to be? Angular position of the, I was going to make up something different, but no, you're right, it's hour. Of the hour hand. Okay, so then let's talk about rates first of all, because this is a good opportunity for us to revisit the concept of a derivative as a rate. So first thing let's do is let's calculate what is dh, I did that backwards. I want to know what is mdh. Yeah. Okay. What's that mean? First of all, don't tell me the answer, but what does that mean? Okay, but I want it in terms of a rate. That's the rate of change of, okay, the angular position of the minute hand with respect to the position of the hour hand, right? Okay. So what is that? Maybe it's easier. Let's do another one too. We'll come back to that one. How about if we did ds dm? Let's start with that one, might be easier. What's that mean? The rate of change of the second hand with respect to the minute hand. Right? So what's it going to be? 60. Yeah, 60. And because the second hand has to go around the clock 60 times for the minute hand to go around the clock once. Everybody agree? Does that make sense? Okay, so that's 60. And what's DH? Or DMDH, sorry. No, it's not 60, it's 12. Right? Because on an analog dial, there's 12 hours on the face of the clock, right? And each time, every time the minute hand goes around once, that represents an hour, right? So it's got to go around 12 times for the hour hand to go around once. Okay. So can you tell me then? And if you can tell me this, you already kind of understand the concept of the chain rule, just intuitively. What is ds dh? 720. How did we get that? Well, yeah, think about that now. If the second hand is traveling around the clock 60 times every time the minute hand goes around the clock once, right? And the minute hand is traveling around the clock 12 times every time the hour hand goes around the clock once, then doesn't it stand to reason that the way we would link those two rates together is by a product? We'd multiply those together, right? So we're going to end up with the M, oh, sorry, took it backwards, the S, the M times the M dH. What do you notice algebraically is happening here? If we write those two rates down, algebraically, yeah, the DMs are canceling, right? So that's one way of writing the chain rule. Like if we want to say, just in general, let's not pin this down to, and so that tells us then, you know, if we get 720, one way to interpret that is that the second hand has to go around the dial 720 times in order for the hour hand to go around once. You could think of it in terms of angular speeds if you wanted to. How many times faster is the second hand rotating than the hour hand? 720. Seems like it'd be more, doesn't it? When you think about it, it just seems like it's, oh, hey, that seems like a long time. But that's it, 720. What's that? I mean, yeah, 12 hours, right? But I mean, that's a long time. So we can write this then. One way to write the chain rule is we can say, just in general, dy du times du dx equals dy dx. That's one way to write it. Okay. It's handy for situations like this, but most of the time, that's really not the way we want to write it. We're going to write it a little differently. So instead of writing dm dh, let's write that as m prime of h. Okay. And what about this right here? This looks like s prime of m. Okay. So another way of writing that would be, and this is going to look a little strange at first, but another way of writing out this product would be to say that this derivative, ds dh, what that's really saying is s prime of what is m? Well, m is a function of, m is being related to h here, right? So if we want to do s prime of m, m is really related to h also, right? So if we want to differentiate this, we'd have to do this in pieces. We'd have to say that this is equal to, let me do it this way. And this is pretty awkward. We're not going to write it this way. I'm just trying to do this so it matches what we did in that first example. What are we doing this? Sometimes in textbooks you'll see this notation. Ours don't do this. But if I do that whole thing primed, if I'm going to do the derivative of that composition, what it ends up being is s prime of m of h times m prime of h. Well, what is s prime of m? S prime of m is 60. M prime of h is 12, and so we get the same 720. Okay? The way we more commonly write that, let's just look at our textbook. Here's the way we more commonly write the chain rule. We write it like that. Let's make that a little bigger. Oh, too big. And this is right out of the textbook. Well, I mean, it works for, you don't have to use clocks. Like in our textbook, I think they use gears. Right? It'd work for same thing. Right? If you're meshing different gears with different radii, you could describe it that way too. But if we look at this version of the chain rule, okay, we already got the top one, right? What about this bottom one? What's this thing? If I've got some function, f of g of x, composition of functions. Let's take a quick second, and before we even go any further, what might that look like? Give me an example of a composition of functions. Who's that for? Oh, that's for
X cubed of x squared. Or x of x.
Okay, what's an example of a composition of functions? I heard somebody, like, what would be an example? Sine of x squared, there's one. If we do sine of x squared, what's the outside layer of that function? I'm doing sine of something, right? And what's inside the sine is an x squared, right? Give me another example of a composition of just two functions. I'll get you started. Square root of
Log of x.
log of x. Outside, what's the outside layer? I've got a square root of something, and inside that function is a log x, right? Remember this stuff?
Yeah.
Okay? So, like if I do f of g of x, let's do it differently. Let's define g of x as being just some function. How about if it's square root of x? Let's define f of x as being e to the x. Okay, so now I want you to tell me, what is f of g of x? Okay, well, let's ask, f of hand is what? F of hand is e to the hand, right? Everybody see that? So if f of hand is e to the hand, I'm getting e to the hand, but the hand is actually g of x, which is a square root of x. Right? See how that works? So if I've got a composition of functions like that, here's how we differentiate it. The derivative of the composition of f of g of x is two parts. There's two links in the chain. I'm going to put the times sign in the middle. The product sign is going to be the red dot, right? The first link is I've got the derivative of the outer layer. And we'll talk about this in class as being the derivative of f of hand is just f prime of hand, right? So we got the derivative of the outside layer times the derivative of what's inside. The derivative of g of x is just g prime of x. Okay, there's an easier way to write this. That looks complicated visually when you write that. And so you have to be very careful with this. I don't want to, I don't want to corrupt you with this one, but this is how we do it in math, seriously. Instead of writing f of g of x, we would write it as, instead, we write it as f of u. Okay, that's f of u. You have to be very careful with this. So we've got the derivative of f of u. If y equals f of u, what is that going to be? Well, we're going to end up with y prime equals f prime of u times u prime, whatever's in the middle, right? So u we always take to be some interior function of x. Okay, let's practice this. So let's try this with a derivative. If we take the function y equals, well, let's just pick one of these. How about this one? If y equals e to the square root of x, what's the derivative going to be? What's the, and you got to kind of always think about this like your functions are complicated, just like onions or ogres, right? We've got layers. You've got to peel them from the outside in. Okay? So, right. So we got to always start on the outside, and we're going to peel the function from the outside in. So the outside layer here is what? E to the hand, right? Or e to the u, you could say if you want to. Let's call it e to the hand. So what's the derivative of e to the hand? E to the hand. So the first layer is e to the hand. What's the next layer? So we're going to put another link in the chain. So now we're going to multiply by the next derivative. You always link the change in the chain rule with as a product. Right? So now we focus inside. What's the next layer? Square root of x.
1 over x.
What's the derivative of square root of x?
1 over the square root.
Almost. That's going to be x to the 1/2, right?
Yeah.
So we get,
1/2 x to the negative.
okay, so 1 over 2 square root of x.
Yes.
Okay. So then we get times 1 over 2 times the square root of x. And so our answer, if I just simplify that, is just going to be e to the square root of x over 2 times the square root of x by the chain rule. Okay? Let's try another one. Let's see, how about if we do something like,
Sine of x squared.
I'm going to do sine of
X squared plus
3x squared minus 2x plus 4. Actually, okay, yeah, we'll do that. Actually, let's make it harder.
Oh.
How about that? Okay, now, don't jump into this. I want you to think about this. How many layers are there to this odor? 3. There are 3, exactly. Okay, now this is tricky because we've written this using kind of a shorthand notation. When we write sine squared of theta, what do we really mean by that? Sine times sine. So when I write, if I write down, in general, if I write down sine to the n of theta, what I really mean is the quantity sine theta to the n, right? Everybody see that? So when you're differentiating, I wouldn't strongly encourage you, at least at first, until you really get the hang of this, until it starts to become very natural, I think I would even rewrite these in that way, because it's much easier to see the layers of the chain rule then. So this really would be the same thing as just saying the quantity sine of 3x squared minus 2x plus 4 squared. So what's the outside layer?
squared.
Yeah, I got hand squared, right? Inside that, I've got
Sine of 3x.
sine of hand, right? Does that make sense? So the outside, if you kind of blur your calculus vision here, from the outside, you've just got something squared. At the outside, it's just a power rule, right? Got the derivative of arm squared. Well, what's arm? Well, if I look inside, arm is actually the sine of hand, right? And then inside the sine function, I've got a polynomial, right? Outer layer is you can't see that part out, but you get the idea. So outer layer, we got a power function. Middle layer is a sine function. Inside layer is a polynomial, right? So how many links are we going to have in our chain? 3, right? We're going to have 3 layers to that derivative. So if we calculate y prime, outside layer, what's the derivative of arm squared?
2 arms.
2 arm, right? 2 arm to the 1. And now we can look inside. Well, what's in there? Okay. It's a sine of a polynomial. So next layer. So we need another link in our chain. Now we look inside. I got the derivative of, what's the derivative of sine hand?
Cosine.
Cosine hand. Right? Okay, we look inside the cosine, and finally, what's the derivative of that polynomial?
6x minus 2.
Okay? That's it. So we're done with the calculus. What's left? Just a little cleanup, right? We would just, what would we probably do here? Probably take the polynomial part maybe out front. So we'd end up with 2 times that. I mean, I don't know, maybe something like 12x minus 4 times sine of this times cosine of that. Right? Just something like that. See, I just got tired of writing. You get the idea. Sine of the polynomial. Okay. How about,
That's 2. That's C.
so I double dog dare you to do this one. We give you a really hard. Let's do. Okay. Okay, try that.
And the x cubed is
Inside.
inside the sign function?
Yep.
Okay.
Try that. You can do that one. You can do any.
Let's go. How do you know? You don't. No, it's all x squared. Dude, that's just working, bro. Look at the x through all that. Read that, it doesn't do yeah, so it's plugging or does it plug in, I guess?
Okay, everybody agree that's, if I write that out, using a bunch of parentheses, that's what it looks like? So outermost level, what do we got here? To fourth power, I got a power function, something to the fourth. Next level, tangent of something. Next level, yeah, exponential function, e to the something. Next level, whoop, something to the 1/2.
Negative.
No, I haven't taken any derivatives yet, right? I've just got something to I've got e to the something. Well, what's that something? That something is a square root, so it's something to the 1/2. Inside the square root, I got a sign. Inside the sign, I got an x cubed. So how many links have we got in our chain this time? 2 many, right? Lots of links. Right?
Would we ever have a problem like that?
I mean,
Like, it's like, plug that into the computer, that's gonna take
yeah. This will, we can do it right now. I don't think it'll take that long. But I probably wouldn't give you that many. That's pretty long.
typing it out.
Yeah, it would take a long time. Yeah. Okay, so let's do this one then. So what's the outer link gonna be?
4.
4 times something cubed, right? So 4 times tangent of e to the square root sine x cubed. Next layer.
Secant squared.
Good, I got tangent of something, so the next layer is gonna be secant squared of all that stuff, right?
Wait, why is it secant squared?
Because the next layer I've got a tangent, right?
Where? What?
So the first layer is here, let's just erase these things one at a time. Right, so if we take the outer layer away, we differentiated the outer layer, then look, we've got, that peels away that outer layer and we're left with a tangent, right? So the derivative of tangent is secant squared, right? So the derivative of tangent hand is secant squared hand. Oops. Oops, I got it backwards, huh? Okay, next layer. If I peel away the next layer, we took away the tangent, right? We differentiated tangent, so now what's left? Yeah, I got e to the hand. What's the derivative of e to the hand? E to the hand. E to the square root sine x cubed. Okay, so we're done with that layer. We got rid of the e. So now what? Yeah, something to the 1/2. Rid of something to the 1/2 is 1/2 something to the negative 1/2, right? Okay, so I'm gonna have to continue over here, so times 1/2 sine of x cubed to the minus 1/2. We peel that layer away.
Did you write, is you want to go to sine
Yeah, we
x
will.
cubed squared?
We will. Yeah, we can simplify all this later. So what's the next layer?
Derivative sine.
Derivative of sine of something is cosine of something, which is an x cubed. And then finally, we peel away the sine, and we get to the last layer, which is 3x squared. So that's our derivative. We're done with the calculus. Now we would just have to maybe clean that up a little bit. Right? And it's not a ton. Just put that on the bottom, put all the constants out front.
You probably just get more complicated than this.
Oh, sure. Yeah.
Where do you find something like this in your life? That big and just.
Well, I mean, with those sound effects, I don't know if you could. It would be like if you were doing, okay, so like in physics, if you were doing, let's say you were doing harmonic motion, where you had some complicated wave function set up on a string, right? If the wave function is, I mean, then you're going to get some kind of a sinusoidal function of some kind of a damped oscillator, maybe. So you're going to have a damping function. You could get stuff like that. I mean, you could. That's quite a few layers. I mean, I kind of contrived that one a little bit because it's so many layers. But you can get lots of stuff going on. Okay. So if I pull all the constants out front, 1/2 times 4 is 2, times 3 is what, 6? So that takes care of all those. I've got an x squared I could pull out front, and I've got this exponential function I can pull out front.
So is there going to be a certain way that you want this inputted into the program?
I mean, not really. I mean, what would you generally, what do you think you would do? You just put the non-trig stuff out front, and then you combine the trig stuff at the end if you can. So I've got a tangent cubed times a secant squared. Probably nothing I can really do with that. I would just get tangent cubed of e to the square root sine x cubed, secant squared, same thing. And then I'm dividing everything by the square root. Oh, I got a cosine too, don't I? Times cosine x cubed, all divided by that. That's my answer. I could really scare my next class if I left that out there.
Please do.
Please do that.
Okay, does that make sense? Okay.
What
I mean,
is
that's the chain rule. So last thing then. So we can take all of our derivative standard forms that we had, and we can turbocharge them with the chain rule. So if we did something like, instead of doing the derivative with respect to x of, for example, x to the n of cx to the n, what would we do instead? We don't want to limit ourselves to just x to a power. We want to be able to do a function to a power, right? So this would become, if we chain rulify that, it's going to be the derivative with respect to x of cu to the n, where u is a function of x, right? And what's our answer going to be? There's just two layers there, right? I've got the derivative of something to the nth power is just cn times something, which is u to the n minus 1, times the derivative of u, which we'll just call, with respect to x, which we'll just call u prime. Right? So that's, from now on, when you actually look in a college calculus book, and you look at your derivative rules, they're going to say this, not this. Right? We start there, but when we add the chain rule, we can expand those. What would, for example, the derivative with respect to x of sine x become, if we chain rulify it?
Derivative of sine u.
Yeah. Derivative of sine u, where u is just, some whatever function of x, is what?
Cosine u times u prime.
Cosine u times, We could write it as u prime, or we could write it as du dx, same thing. Different books will write it different ways. I prefer to just write u prime, it's a lot easier. Right? Okay, what's the derivative with respect to x of e to the u?
E to the U times U prime.
Right? And just in case, just so that, you know, kind of link that back to what we're doing. If y equals e to the x squared, what's y prime equal? Times 2x. 2x out front, right? That's what this tells me, right? Okay? Enough for one day?
Yes.
Okay?
Please leave out that horrendous equation in the next class.
Tell them that they have to solve for x. One for y equals 0.
Do that, yeah,